नमस्कार दोस्तों, वेलकम टू गेट वाला। मैं हूं सतीश कुमार दुरिशेट्टी, फैकल्टी ऑफ ऑप्टिकल इंस्ट्रूमेंटेशन। मैं आप सब लोग को स्वागत कर रहा हूं हमारा रेगुलर यूट्यूब सेशन को। ओके, सो यूट्यूब सीरीज पर हमारा ऑप्टिकल डिटेक्ट चल रहा है। सो ऑप्टिकल डिटेक्टर्स हम डिस्कस करेंगे। सो लास्ट क्लास में हमने ऑप्टिकल सोर्सेज डिस्कस किया था, उस पर हमने एलईडी का इंटरनल क्वांटम एमिशंस के ऊपर भी क्वेश्चंस करवाया था। सो अभी हम डिस्कस कर रहे हैं ऑप्टिकल डिटेक्टर्स। Okay, so today we are going to discuss variable detectors. What are the detectors we are going to discuss? So we are going to discuss the UV detectors, visible detectors and IR detectors. So these are various numericals are also possible. One of the important topic with respect to GATE examination. अगर आपने लास्ट 5 साल का गेट का क्वेश्चन देखे तो हमको लगभग हमेशा 1 मार्क और 2 मार्क्स का सवाल आ रहा है ये टॉपिक से, ऑप्टिकल डिटेक्टर से। सो जितने लोग लाइव में हैं मुझे एक बार कंफर्मेशन कर दीजिए ऑडियो वीडियो सब कुछ क्लियर या नहीं। ओके, चलो लेट अस स्टार्ट फ्रॉम द सेशन नाउ। Optical detectors. So what is the optical detector? What it will do? See here. What is the optical detector? What it will do? So if you see the optical detector, what it will do? It will take a radiation, it will convert it to electrical. So it will take a radiation, light into electrical quantity. It will convert light into electrical output. Light into electrical output. Okay. So UV detectors will convert the UV radiation. Visible detectors convert the visible radiation. IR detectors will convert the IR radiation. So what a UV detector will do, what a visible detector will do, what a IR detector will do, let us see here. So if you see the UV detector, it will convert the UV radiation into current output. Similarly, what is a visible detector will do, it will convert the visible radiation into current output. What is the IR detector will do, it will convert the IR radiation into current output. Okay, in short if you see UV detectors का example photo emissive cells, visible detector के examples photodiode and LDR. IR detectors का example bolometer. So have a note of these points. जल्दी से जल्दी नोट कर लो बेटा, हम स्टार्ट करेंगे सेशन को। Done? Noted? Yeah. Now let us start. First, directly we'll go for the most important detector, that is the visible detectors. Why? Because visible detectors, LDR and photodiode, they will play a major role in understanding Yeah. So first let us start with visible detectors. In the visible detectors, first most important is the visible detector. Why? Because in our regular life we are using this. Visible detectors will convert the visible radiation into current. Okay. So under the visible detectors we're having materials, semiconductor materials. So semiconductors materials will work like this. Semiconductors. So what are the semiconductors? The semiconductors are germanium, silicon and selenium. So these are the semiconductors. These are the semiconductors. Okay. So the examples for the visible detectors are LDR, and photodiode. LDR and photodiode. So how the LDR will work and how the photodiode will work. So if you see the LDR, first one, LDR stands for light dependent resistor. LDR stands for light dependent resistor. Light dependent resistor. So as the intensity of the light is increasing, the resistance goes on decreasing exponentially. So now if you see, as the intensity of the light is increasing, the resistance goes on decreasing exponentially. So when the intensity of the light is equal to 0, so here we'll be having the dark resistance. When the intensity of the infinite, we're having the shine resistance. Shine resistance. Dark resistance and shine resistance. So please make a note of this. So materials, if you see the materials for this, cadmium sulfide, cadmium selenide, lead sulfide, lead selenide, lead telluride. Okay, so please make a note of these points. Noted? Chal. So when there is no light, the intensity of the light is equal to 0, the resistance is very, very high. So that resistance is called dark resistance. Dark resistance will be very, very high. So that will be in the range of 100 kilo ohms. But when the light falls on the semiconductor, what happens? So as you know, when the light falls on semiconductors, what happens? When the light falls on the semiconductors, what happens? So the energy gap will be there. This is E1, this is E2. So this energy gap, which is E2 minus E1, units are electron volts. So here the electrons are waiting. So once the light touches, the light makes, intensity of the light touches, these electrons will start moving up. These electrons will start moving up like this. So now here comes, electrons will come here, and these are the holes. Okay, so electrons are coming and holes are moving. So this is what we call as EHP combination. That means electrons started moving. So when the light intensity is increasing, electrons start moving. So that is what we call as conductivity is increasing. So resistance will decrease. So this phenomenon is called photoconductive effect. This phenomenon is called photoconductive effect. Okay, so please make a note of this. So LDR is also called as photoconductive cell, or it is also called as photoresistor. Okay, so please note down. It is also called as optoresistor or optoresistor also we can say. You can also say it as optoresistor. Okay dear, chalo. Make a note of this. And the resistance at a particular time, if you see this resistance at a particular, if I want, so this resistance at a particular time I want, so the resistance at a particular time I want, so resistance at a particular time is equal to R final plus R initial minus R final into e power minus t by 2. R final plus R initial minus R final into e power minus t by 2. Okay, so that is what the LDR will work. So LDR is one of the important thing. Yeah. Next comes the photodiode. Next comes the photodiode. Suppose we can have a question here. A question. A LDR whose initial resistance is 100 kilo ohms at dark conditions. Under the maximum illumination, the resistance is 100 ohms. The time constant, why? Because LDR is a first order system. The time constant of LDR is 150 milliseconds. The question is, what is the resistance of LDR just after 80 milliseconds of focusing light? Please note down. आंसर कितना आएगा? LDR whose initial resistance is 100 kilo ohms. Dark condition. So see here. So first to draw the diagram like this. So this is LDR diagram. So initially this is at a intensity of the light is equal to 0. So at that moment there is a resistance called dark resistance. So the dark resistance was how much? 100 kilo ohms. Now at an infinite time it is having a minimum resistance, which is what we call as shine resistance. So now it is moving down like this. LDR whose initial resistance is 100 kilo ohms, and here it becomes as 100 ohms. So at a particular time it is asking, at a time of how much? 80 milliseconds, and the tau is given as how much? 150 milliseconds. So it resembles the it resembles the capacitor discharging curve. So we can write the equation: resistance at a particular time is equal to resistance at final, which is infinity, plus resistance at initial minus resistance at final into e power minus t by 2. Okay. We need that resistance at final, that is 100 ohms, plus initial resistance, that is 100 kilo ohms, minus final resistance, that is 100 ohms, to e power minus t. What is the t? Time is equal to 80 milliseconds, and tau is 150 milliseconds. So milliseconds gets cancelled. So now if you simplify, this is 100, this is 100k minus 100. 100k means 100,000. 100,000 minus 100. So that is 9999 999 000 e power minus 80 divided by 150, 0.586. So this is 0.5866 into 999 plus 100. So divided by 1000 karo, in kilo ohms you are getting 58.6. So resistance at a particular time is equal to 58.7 kilo ohms. Got it? So please make a note of this point. Chalo. Now let us go for the next one, photodiode. Next topic is the photodiode. Photodiode is nothing but a reverse bias PN junction diode. So in forward bias PN junction, how it works we know very well. So now if you see photodiode, how it works. So this is the photodiode diagram. See here. Photodiode, what it will do, it will convert the visible radiation into current. It will convert the visible radiation into current. So it is a reverse bias PN junction diode. In the forward bias, the conductivity is good, all we know that. In the forward bias, the conductivity is good. Okay. So this is the forward bias. So this is a cut-in voltage. So up to the cut-in voltage, it is having some minimum time to pull off. Why? Because the charge carrier density takes time. Then after, in conductivity starts. In forward bias, it is just similar to our PN junction diode. So there is, in reverse bias, it is a reverse leakage current, small, minor. Why? Because depletion width increases. So the point here is, in the reverse bias there is a depletion width increment, but now if I focus the light, then there is a possibility of conduction. So now if I focus the light here, so this is the depletion width. So the capacitance is given by Cj. So Cj is equal to epsilon naught epsilon r A by W. So that is the capacitance. Why? Because the depletion width increases now. Its side, this side some negative region, this side some positive region. Why? Because the holes are attracted, the electrons are attracted here. Okay, so the width increases. So Cj is equal to epsilon naught epsilon r A by D. D means W. Okay, so Q is equal to C into V. So C is equal to junction capacitance, V is the DC voltage. So I is equal to dq by dt. So d by dt of this C into V. So C if I take out dV by dt plus V if I take out dC by dt. So this one DC voltage, this is a constant. So constant means it will be 0. Okay, so now if you see, this is a scenario, reverse current scenario, V into dC by dt. So there is a possibility, even though this is a constant, but if there is a change in possible here, there is a current possibility is there. So to make the change in the junction capacitance, at no light, junction capacitance is epsilon A by W, no charge carriers, depletion is same. So at no light, this is constant and this is also constant. So that's why dC by dt is equal to 0. So at no light, I reverse that is equal to 0. Now ideally, I reverse is equal to 0. So practically the reverse leakage current, I diffusion, I reverse leakage is equal to I dark. So this is what we call as static current. Okay, static current. But when the light falls on it, what happens? This light makes the waiting electrons at the ground to jump up. Okay, the waiting electrons at the ground, they are going to jump up. So because of that, the charge carrier density increases. Slowly the electrons are moving up. Okay, so when the electrons are moving up now, so conductivity starts, charge carrier density increases, so the depletion width decreases. Okay, so charge carrier density is increasing, so dC by dt is equal to this. So slowly the width decreases, minus epsilon I by W square dW by dt. So now the current is possible. Why? Because current is equal to Q is equal to CV, I is equal to dQ by dt. So C into dV by dt, V into dC by dt. Now in this scenario, this dC by dt can be possible. Even though VDC is constant, that term will become 0, derivation of this, but this one minus epsilon I by W square W by dt. So the photonic current is proportional to the rate of change of depletion with respect to time, and is also proportional to rate of energy with respect to time, is also proportional to optical power. Okay, so that's how the photonic current starts. The more is the optical power incident, the more is the rate of change of energy, the more is the rate of change of depletion width. Accordingly, photonic current will be developed. Okay, so now this photonic current will be possible because of the light. So the more is the number of photons incident, the more is the number of EHP generated. Okay, so the quantum efficiency of the photodiode is given by number of EHPs generated divided by number of photons incident. That is what we call as quantum efficiency, number of photons EHPs generated. Why? Because photons are incident, EHPs are climbing now. So input is this, exactly opposite to LED. In LED we are giving the current, we are injecting the EHPC, in return we are getting the light. Photons are coming, but here is entirely opposite. We are giving the photons input and we are getting the current output. Okay, chalo. So this is a quantum efficiency derivation. So please go through, exactly opposite to the LED topic. Okay. Have you noted this? So quantum efficiency of the photodiode, I can take it as number of EHP generated per time by number of photons incident per time. Photons are incidents and EHPs are generated. So this is the rate of EHP by rate of photons. Okay. So quantum efficiency of the photodiode is rate of EHP by rate of photons. Exactly opposite to LED derivation. So rate of EHP, I can take it as IPH by Q, okay, and P optical by energy of the photon. So this is IPH by Q and this is P optical by energy of the photon. So this is IPH, P optical. If you take IPH by Q, CPH by photon. So this particular one is called as responsivity. So responsivity is equal to IPH by P op. So units are ampere per watt. So rate of EHP is equal to IPH by Q, rate of photons is equal to P optical by energy. So this is rate of EHP, this is rate of photons. Okay, so let us now responsivity is nothing but how much photocurrent generated as output, but how much incident is the optical power. So these are the important formulas for the photodiode subject. These are the important formulas. So from these formulas only majorly the questions will be coming. So if you are clear about these derivations, it will be easy. Rate of EHP by rate of photons. So rate of EHP is given as IPH by Q, rate of photons is given by P optical by energy of the photon. So internal quantum efficiency of the photodiode is IPH by Q by P optical energy photon. So IPH by P optical, EPH by this IPH by P optical, you can take it as a responsivity. Okay, so now let us go for some questions now. So there are a good number of bunch of questions on the photodiode. So let us move for the photodiode questions. Yeah. So try to answer this question. These are the previous year gate questions. Solution. Optical pulse containing 6 into 10 power 6 photons, instant and a photodiode, and 4.5 into 10 power 6 EHPs. Okay, so this is the photodiode. So internal quantum efficiency is 4.5 into 10 power 6 divided by 6 into 10 power 6 into 100. Okay, 75% is the answer. Correct answer is 75. I didn't get the response. What is the purpose of taking the YouTube class? So let us go for this question next. Yeah, answer this question. Answer this question. See here, a pin photodetector has a junction capacitance 16 picofarads, active area of 10 mm square. So this is the active area of 10 mm square, and responsivity of 0.5 ampere per watt. Responsivity of 0.5 ampere per watt. It is illuminated by a light of intensity 1 milliwatt per centimeter square. Intensity of the light is 1 milliwatt per centimeter square. A voltage output is obtained by connecting 100 kilo ohms. So first of all, we have to find out. So for 1 centimeter square, 1 milliwatt, 1 centimeter is equal to 10 mm. 10 mm whole square, 1 milliwatt. So 100 mm square, 1 milliwatt. So 10 mm square key, how much divided by 10? 0.1 milliwatt. So this is the active optical power. So responsivity is given in the question as how much? 0.5 ampere per watt. 0.5 ampere per watt. For 1 watt, 0.5 ampere. For 0.1 milliwatt, 0.5 into 0.1, 5 by 10, 1 by 10, 5 by 100. So 0.05 milliampere. So now this goes to the RL resistor, 0.05 milliamperes. So RL is equal to series 100 kilo ohms. 100 kilo ohms. So voltage is asking, so VL is equal to I into RL. So that is I is equal to 0.05 milliamperes, 10 to the power minus 300 kilo ohms. So the answer is 5 volts. So please make a note. हेलो, क्या है यार, आपको कब आना है? क्लास एंडिंग समय पे आ रहा है कि आपको पता नहीं है? सूर्यदीप कुमार, ओके, कहाँ गए आप? चलो, लेट अस गो फॉर द नेक्स्ट क्वेश्चन. आंसर दिस क्वेश्चन. ये 2012 का सवाल है. response for the photodiode is given as, so कितना दिया responsivity, so responsivity कितना दिया रे, so if you see the responsivity, so see here the responsivity is given as how much, the responsivity is given as 0.9 ampere per watt, 0.9 ampere per watt. Okay, so V out is equal to what, here is a negative terminal, so minus RF into I photodiode. So RF we don't know, V out is given as minus 1 volt, so power is 1 milliwatt. So for 1 watt 0.9 amperes, so for 1 milliwatt how much, 0.9 milliamperes. So this is 0.9 milliamperes. RF we don't know, so this is 0.9 milliamperes. The V out is equal to how much, minus 1 volt. So minus 1 gets cancelled, so RF is equal to 1 by 0.9 to 10 power minus 3. So 1000 by 0.9, that means 10,000 by 9. 10,000 by 9. Okay, so 10,000 by 9, what is the answer? Yes यार, आप आंसर बताओ ना, divide by 1000 करो, so we are going to get 1.11 kilo ohm. Am I right? Check it. Option D is the right answer. आंसर कितना आया, 1.1 आ गया, ऑप्शन डी आ गया ना, 0.9 कैसा आता है? Got it? Answer clear आ गया? चलो, let us go for the next question. चलो, let us go for the next question. Answer this question, last question for the day. Answer. Chalo. A photodetector circuit is given in the figure. The photodiode has an active area of 10 power minus 2 meters centimeter square. So this is the active area, 10 to the power minus 2 centimeter square. Sensitivity is equal to 0.5 ampere per watt. Light of intensity 10 milliwatt per centimeter square. So this is 10 milliwatt per centimeter square. Falls on the photodiode, the output V0 is equal to dash. So he has mentioned here 10 milliwatt per centimeter square. So for 1 centimeter square area, 10 milliwatts of light is falling. But the active area is how much? The diode active area here is 10 to the power minus 2 centimeters. क्या कर रहे हैं यार आप आंसर नहीं बोल रहे? आंसर कितना आ रहे सूर्य प्रताप? सूर्यदीप. Yeah, 1 centimeter square की 10 milliwatts. Now 10 to the power of minus 2 centimeter square into 10, that is 10 to the power of minus 1 milliwatt. So the answer is 0.1 milliwatt. So this is active optical power, 0.1 milliwatt. Okay, and the sensitivity is given for 1 watt. How much current? 0.5 amperes of current. Next for 0.1 milliwatt, how much current? 0.1 into 0.5, 1 into 5, pi by 100. So 0.05 milliwatts. Next. So question asked is V0 per milliampere, sorry, milliampere. This is milliampere. So what is the V0? V0 is equal to minus RF into I. Minus RF, that is minus 100 kilo ohms, into I. What is I? That is 0.05 milliamperes. Okay. Chalo, 10 power minus 3, 10 power gets cancelled. So answer is minus 5 volts. The answer is minus 5 volts. That's it. Okay. So these are the topics, my dear. I hope you have enjoyed the session. Any doubts you can ask me. You are from which college? You are from instrumentation background? Thank you.